All right, and we're back for the Thursday slash Friday edition of MA 341. It's been an exciting day out here. I'll show you. So I got these oh, gymnastics rings in the mail, which are now securely anchored to this ceiling joist here. However, just this morning, they weren't so securely anchored. So I initially had them put up with an old bicycle hook, the kind of thing you would hang a bicycle in your garage with. And it turns out that bicycle hook was kind of fatigued through repeated use and gave way in the middle of an exercise. Fortunately, I had the presence of mind to use my face as a brake. So, no harm, no foul. In honor of the absent hockey season, I'm trying to grow the playoff beard here. Although the beard is not an N95 approved facial hairstyle, because it prevents the proper seal. For that, you need the goatee with pork chop sideburns. But thanks to the miracle of Instacart, I never have to leave the house, so we're good there. What else is exciting? Oh yeah! So finally, all the goods arrived from my home climbing wall. So that's getting assembled this weekend, which more than anything will give the kids something to do. And what better way to entertain children than power tools, right? What could go wrong? All right. So, last time, I've left it up on the board here, we were discussing this notion of uniform continuity, okay? And what I was trying to explain with these two pictures is the idea that when we talk about continuity, the usual continuity, it always is a discussion about the continuity of the function f, say, at a fixed point c on the x-axis in the domain, okay? And then the question is always, if you take f of c and you take a little horizontal tube here, it's going to have width 2 epsilon around f of c, then you ask yourself, I go over and hit the function, how wide of a vertical tube do I have to sit inside over the x-axis there to make sure that when I go up and hit the function, I wind up inside the original prescribed horizontal tube? And the observation was that in the case of the function f of x equals x, the relationship between how wide the vertical tube is and how wide the horizontal tube is steady, right? And in fact, it's 1 to 1. I mean, if the width is 2 epsilon here, the width over here is going to be 2 epsilon as well. Whereas over here, in the case of the function f of x is equal to 1 over x, this is no longer the case, right? So I have two function values here, f of c1 and f of c2. If I take a little horizontal tube, well, you can hardly see it. It's really right there. Little horizontal tube around f of c1 and the same width of horizontal tube around f of c2, then I have a lot more latitude width-wise in terms of a vertical tube that I can use to go up, hit the function, and then wind up in the little horizontal tube for f of c2. Whereas over here, because the function is very, very steep, the corresponding vertical tube is extremely narrow around c1, okay? So, given an epsilon greater than 0, you can find delta such that blah, 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 blah. But the point is that the delta really depends heavily on the value of the function that you're considering in the case of f of x equals 1 over x, whereas it doesn't really depend at all on the value of the function over here, okay? And that is the difference between a uniformly continuous function and a not uniformly continuous function. So again, let me write down Oh, well, I don't think I even did in the first place. Let me write down the formal definition here for uniform continuity. So, definition. F from A to R is uniformly continuous on A if for all epsilon greater than 0, there exists a delta greater than 0. I think I did do this. Such that f of x minus f of y is less than epsilon if x and y, which are in the domain, if they satisfy that the distance from x to y is less than delta. Okay? And the point is that there's no longer a fixed point C. We're not talking about continuity at C. We're talking about uniform continuity, and it is on the entire set A, on the entire domain A. Okay, and as we shall see, your choice of domain can severely affect whether or not your function is uniformly continuous on A or not. Okay, you can have exactly the same function, right? So we'll have an example in a moment, the function f of x equals x squared, where we will be able to see that that function is uniformly continuous if it's defined, say, on some closed bounded interval, and it is not uniformly continuous if it's defined, say, on the whole real line. Okay? All right, so that is the official definition of uniform continuity. Given epsilon greater than 0, there exists a delta such that, and then the difference is that it's f of x minus f of y less than epsilon, where x minus y is less than delta. I guess that looks exactly the same as the definition of continuity, except that you've replaced your c with y. But the point is here that it's for any x and y in A that satisfy this condition. Okay? No restriction otherwise, other than the distance between them is less than delta. All right, get some coffee. Oh. I can only imagine how incredibly costly it would be if you were already, before this crisis, like really into some sort of expensive narcotic. I mean, coffee is pretty much my only vice, and I am drinking a lot of coffee, I gotta tell you. Pretty squirrely by this point in the day. All right. So let's have some examples. So let's take our first example, the one that I put on the board, which is that f is a function from the reals to the reals. It's just the identity function. F of x is equal to x. So, if epsilon greater than 0 is given, this is going to be a little fast and loose. Let's choose delta to be simply equal to epsilon, right? That's what I was saying as I was gesticulating in front of that picture, was that, the distance, around the function value is the same as the distance around the x value. Okay, so if we choose delta equal to epsilon, then the condition that x minus y is less than delta, which is equal to epsilon, means, of course, that f of x minus f of y, right? So if x minus y is less than delta, we want f of x minus f of y to be less than epsilon. But f of x minus f of y is exactly equal to x minus y in this very simple example, okay, which of course is less than delta, which is equal to epsilon. And that does the trick, okay? So f is uniformly continuous on R. Okay? Right. Now, if a function is uniformly continuous on some set, in this case R, and then you want to consider the function restricted to some smaller domain, so we just think about this function f on some subset B of R, then it will still be uniformly continuous on that subset B. Okay, so uniformly continuous on a big set means the function stays uniformly continuous on a smaller set. Okay? The opposite we shall see is not true. Uniformly continuous on some smaller set does not necessarily mean the function will continue to be uniformly continuous on a larger set. So let me just make a note of that. Let's see, so notes. If f from A to R is uniformly continuous on that set A, and you consider some set B subset of A, then f is uniformly continuous on B as well. Okay? So uniform continuity passes from a big domain to a smaller domain. Okay? The next example will show that the converse is not true. Okay? So let's take, for example, now, f is going to be a function. I'll restrict it to the non-negative reals, and it's just going to be the function f of x is equal to x squared. All right. So, without getting too formal straight away, let's just have a look at this situation. Right? So, let's look first at f of x minus f of y. That's the thing we ultimately would like to make small, to make less than epsilon. And we have a formula for f, so this is the same as x squared minus y squared, which can be factored as x minus y times x plus y, absolute value in each case. And this is good, right? Because if you would like to make that thing over there, the absolute value of f of x minus f of y, small, less than epsilon, and the only thing you're allowed to control is the distance between x and y, right here, then it's nice to have an algebraic expression which connects the thing you want to make small with the thing you can make small. And indeed, that's the same game that we play when we're looking at continuity. All right? And again, as is the case when we're looking at continuity, you can run into some problems because on the one hand, yes, you can control this guy here, but you've got this other piece over here, right? And if you don't have any control over how big that is, it's hard or impossible to say how small this guy has to be in order to get you less than epsilon, okay? So without writing down all the details, what I'm going to point out is that there's just no way, if I say let's say I wanted this distance to be less than 1, okay? That means that this product here always has to be less than 1. And that has to work for all x and y in the whole domain, right? And that domain is all the real numbers from 0 to infinity. So this could be 17 million, and this could be 17.5 million, which makes 34.5 million right here, which means that this has to be strictly less than 1 over 34.5 million to make the whole product strictly less than 1. And then you can rapidly see that the bigger you make x and y, the smaller this guy has to be in order to make the product less than 1. And that's a no-no for uniform continuity. It cannot be the case that the distance required between x and y depends on what x and y are. It has to be a universal distance between x and y, no matter what x and y are. Okay, so roughly speaking, this thing fails to be continuous because the domain is too big. Okay, and the function x squared, right? I mean, if we look at it, there it is, more or less, right? The idea is that as x gets bigger and bigger, the function gets steeper and steeper and steeper. And as we saw in that pictorial example at the beginning of class for the function f of x equals 1 over x, it's exactly when you get this kind of behavior, when the function gets steeper and steeper and steeper, that you lose this ability to be able to say uniformly how close together x and y have to be in order to get the function values close together. Right? The steeper this thing gets, the closer x and y have to be in order to get the function values to simply stay less than 1 apart. Okay, so so this is not uniformly continuous. But it's not uniformly continuous, so what I would like to point out also is that it's not so much just, I mean, it is the behavior of the function, but it's also the fact that I can make x and y as big as I want, right? What if I couldn't make x and y as big as I wanted, all right? So let's consider exactly the same situation, exactly the same example, except let's change the domain. Let's insist instead that the function f has for a domain the bounded interval, bounded closed interval from 0 to 1. Okay? Well, now, draw a new picture for starters. Here's 1, and here's 1. And my function looks kind of like this. Right? And so once again, yes, the function gets steeper and steeper and steeper, but there's a limit to how steep it gets, right? And how steep it gets is, well, I mean, it's getting steeper and steeper. So whatever the derivative is here at x equals 1, that's the steepest it gets. Okay, so you have some control over how steep it gets. And that's reflected in the fact that if you want f of x and f of y to be close together, well, this little string of equality shows you that, of course, this has to be relatively small. But this thing here, which was problematic before because it could be arbitrarily big, is now not a problem anymore, right? Because that thing there is now less than or equal to 2 times absolute value of x minus absolute value of x minus y, right? The biggest that either of these guys can be is 2. Or sorry, 1. Therefore, the sum cannot be bigger than 2. Okay? So that means, so given epsilon greater than 0, we would choose delta to be equal to epsilon over 2. Right? And then what our little algebraic derivation there tells us is that if the distance from x to y, absolute value of x minus y, is less than delta, which is equal to epsilon over 2, then the distance from f of x to f of y, as shown here in the first 2 lines, is less than or equal to 2 times absolute value of x minus y, which is less than 2 times epsilon over 2, which is epsilon. Okay? And that works for all possible x and y in the domain, where the domain now is the closed and bounded interval from 0 to 1. Okay? So we had the same function, but depending on what we chose the domain to be, the function was either not uniformly continuous or it was uniformly continuous. Okay? Uniformly continuous functions have to be continuous. Okay? Maybe I should have made a note of that sooner. So uniform continuity is definitely tougher, stronger than plain old continuity. And I guess that should already be plain because we certainly have already in this class proved that the function f of x equals x squared is continuous everywhere, right? In fact, any polynomial is continuous everywhere on the entire real line, okay? However, even just plain old f of x equals x squared fails to be uniformly continuous even on half the real line, okay? So it is significantly tougher to be uniformly continuous, which I will summarize here. So note, if f is uniformly continuous on A, then f is continuous at every point C belonging to A. Okay? So it does go one way. Uniform continuity implies continuity. Continuity does not imply uniform continuity, as we have just seen in the case of the function f of x equals x squared. All right. So I also want to give you an example, explicit with technical details, of non-uniform continuity in the case of the second example that I drew a picture of, which was the function f of x equals 1 over x. And for that, before we get to that, I need to provide you with a criterion for the failure of uniform continuity. So I've given you the definition of uniform continuity. I've told you what it means to be uniformly continuous. Now I'm going to tell you what it means to fail to be uniformly continuous. I'm going to give you the sequential characterization of the failure of uniform continuity, because that is the characterization that is most practically useful. Okay, that's typically the way that you would take an example. If I gave you an example on a test and I said, here, this is not uniformly continuous, explain why. Show me why. This is what you would employ. Okay, so just fact, I guess. It's just a consequence of the definition of uniform continuity. So f is not uniformly continuous on A if there exists some epsilon naught greater than 0 and two sequences xn and say un in the domain A such that on the one hand xn minus un goes to 0. Okay, so these two sequences, whatever they are, have the property that the elements of these two sequences are getting closer and closer together. Caution here, this does not mean, and indeed it need not be the case, that either of xn or un actually converges. Okay? It's entirely possible for two sequences to fail to converge and nevertheless get closer and closer together to each other. They're just, they're going to hell in a handbasket together. All right? So, you have, if there's an epsilon greater than 0, epsilon naught, greater than 0, and sequences xn and un in the domain A such that the distance from xn to un is going to 0, yet f of xn minus f of un, that's greater or equal to epsilon naught. Okay? In other words, the distance between the function values on these two sequences, they stay far apart. So the points are getting closer and closer and closer together, but the function values are staying far apart. That's the failure of uniform continuity. Okay? All right. So how do we see this in action? Well, and maybe I should point out, the sort of dissimilarity. If I just wanted to say that a function was not continuous at some point, okay, then I would adjust this statement here. Oh, I'm gonna sneeze. Oh boy. Oh my goodness. Okay. If I just wanted to say that f was not continuous at some point, say C in the domain of A, then all I would do is take this very definition here, and instead of un here, I would just take the constant sequence equal to C. So replace all the un's with C. And then you would have the definition of the failure of continuity, because you would have a sequence xn converging to C such that f of xn does not converge to f of C. Okay? But here the failure of uniform continuity means you even need to allow for these two sequences, xn and un, to move around all over the domain. Okay? And nevertheless have this fail. Okay. And of course, as I said, if something is uniformly continuous, then it has to be continuous. Therefore, if it fails to be continuous, it definitely fails to be uniformly continuous. Right? But, okay. That's part and parcel with this fact here. All right, so let's see this in action. So, for example, let's now consider f of x equal to 1 over x, and domain will be, just the non-negative, or the strictly non-negative, if you like, real line, the open interval from 0 to infinity. Okay? So I claim, and I did claim earlier when I was trying to explain all this, that this function here is not uniformly continuous. Okay? So now I would like to give an example of that fact. So let me see. So so of course you kind of have to know where you're going to get started, but let me take epsilon naught equal to 1. All right, so I'm going to try to show that this function is not uniformly continuous, and in order to do that, I will have to exhibit two sequences that are getting closer and closer together, which nevertheless have the property that their function values on those two sequences are staying far apart. So let's let xn be equal to 1 over n, and un be equal to 1 over n minus 1. All right. Then, if you want to look at the distance from xn to un, well, that's less than or equal to, by the triangle inequality, 1 over n plus 1 over n minus 1. And this clearly goes to 0. Right? So, at the very least, these two sequences, xn equals 1 over n and un equals 1 over n minus 1, they satisfy this feature of the failure of uniform continuity. The two sequences are getting closer and closer together, because in fact they're both converging to the same point, namely 0. Okay? Now, f of xn minus f of un, that just means that we take each of xn and un and plug them into 1 over x. Right? Well, that means that I'm going to get that f of xn minus f of un is equal to n minus n minus 1. And that's always equal to 1, which is the same as epsilon naught, which is greater than 0. Okay? So on the one hand, we've got these two sequences, xn and un. They're getting closer and closer together as required. Okay. On the other hand, if we take those two sequences and plug them into our function, f, then f of xn minus f of un is always, in fact, just equal to 1. They're staying far apart. Okay? And that tells you that this function fails to be uniformly continuous on its domain. All right. So there should be some sort of, I guess hopefully you got the impression from this example with f of x equals x squared that, of course, while continuity is important, continuity of the function f is not enough to get uniform continuity on a given domain. And moreover, the domain makes a pretty big difference to whether or not you've got uniform continuity, right? So for x squared, it was uniformly continuous if we just had the domain as the closed bounded interval from 0 to 1. And it was not uniformly continuous if we had the domain as the half-open interval or half-closed interval from 0 up to infinity. So that brings us to sort of the big theorem, for us at least, regarding continuity versus uniform continuity. And what it says is that a continuous function on a closed and bounded interval is automatically uniformly continuous. Okay, so theorem. F from the closed bounded interval a comma b to R is continuous on the entire interval, meaning at each individual point in the interval, the definition of continuity is satisfied. Then f is uniformly continuous on that same interval, a, b. Okay? So uniform continuity is automatic from continuity, provided that the domain is a closed bounded interval. And as with so many things in this course that involve closed bounded intervals, this is just a special case of the fact that the closed bounded interval is one of these what we call compact sets. So the big theorem is that continuous functions on compact sets are automatically uniformly continuous, but our favorite example of a compact set is the closed bounded interval from A to B. Okay, and so here, I'm kind of at odds with myself over what to do. Because I know that if I start the proof now, I will not finish it in time for the end of this lecture. And I really hate when it comes to a complicated and involved, the ideas in the proof are not difficult, so in some sense it's less technical than the sort of max-min theorem proof or especially the intermediate value theorem proof. At the same time, it is kind of long, and I want to make sure that I write all the details down carefully, and I don't think we'll be able to squeeze that into 10 minutes. So, in a kind of Friday afternoon sort of spirit, what I'll do is explain roughly how the proof goes here, and then we'll probably cut it a little bit short today. And then for Monday's lecture, I will go through the proof in detail. And then next week, of course, is our last week of sort of new stuff, instruction, and I will post assignment 10 tonight. or tomorrow, one of the two. And that will be the last assignment for the year. Okay? So assignment 10 to be posted tonight or tomorrow, whenever this video gets posted, etc. That's going to be the last assignment for the whole year. Oh, right, and things are graded there, like I say, and if for some reason there's a technical glitch or problem, please do get in touch with me. I've been trying to stay on top of the email. Right. Okay, so the rough idea of the proof. So proof, I guess, in quotation marks, it's by contradiction. Okay, so the idea will be we assume f is continuous at every point in the closed bounded interval AB, but that f is not uniformly continuous. Okay? So then we say f not uniformly continuous. Well, what does that mean? Well, we just finished discussing it at length. That means we're going to get these two sequences, xn and un, and xn and un. They're getting closer and closer together. Okay? But their function values are going to stay far apart. Right? Now, what we want is for this to somehow contradict basic continuity, right? Because that's the fundamental assumption, right? Is the domain, closed interval from A to B, and the fact that f is continuous at every point in that domain. So we would like this thing to somehow contradict continuity at some point in the domain of the function. The problem is that in general, these two sequences, xn and un, they don't have to converge. Like I said, all they have to do is get closer and closer to each other. They can be wobbling back and forth together inside that interval from A to B to their heart's content and never settle down. So this is where the fact that you've got a closed bounded interval comes in, right? Because what that means is that whatever else they may be, both sequences, so let's say xn in particular, xn is a bounded sequence, right? And so the Bolzano-Weierstrass theorem says that every bounded sequence has a convergent subsequence. So what we're going to do is say, well, since this guy has a convergent subsequence, I can go ahead and at least assume that the xn's are converging. By just passing to the subsequence, I'll assume these guys are converging and that they're getting closer and closer together. And then by a relatively straightforward but careful argument, you can show that if they're getting closer and closer together, and if this guy is converging, well then, this guy has to converge too, and moreover, has to converge to exactly the same thing as this guy. So in other words, we're going to take these two sequences, provided by the assumption that we are not uniformly continuous, and from them, using the fact that our domain is a closed bounded interval, we're going to prove that in fact we can go ahead and assume that xn and un do actually converge, and both converge to the same thing. Once we have that, then we will be able to prove that this statement here, that these guys getting closer and closer together, even though their function values stay far apart, that contradicts continuity, because we have the extra assumption that those two guys are convergent. Okay? So that's how the proof is going to go. But in there are a lot of kind of triangle inequality arguments and careful arguments about convergence of sequences. And like I say, if I had started it, I wouldn't have been able to finish it, and I have to pick it up halfway through. And that's just pedagogically unsound. All right, so like I said, I'm going to cut it a little bit short here. Since it's Friday, it's sunny, it's cold here though. I don't know, hopefully it's warmer wherever you are. Yeah, we will pick this up. We'll pick up the proof of this theorem on Monday. Wash your hands.